Hello everyone, we are going to start a series of lectures on techniques of limit computation. So the first technique we will be talking about is called direct substitution method. I'm going to explain it, and then after this method we're going to talk about the other techniques of limit computation in the next series of lectures. So we have limit of a cubic function here, limit of x cubed minus x squared minus 4. When x approaches 2, we want to find that limit. So what we're going to do, we are going to use the properties of limits, which we have already learned in the past. So we're going to say this is basically in the form of sum or difference of few functions, x cubed, and then we have minus x squared. That's a cubic function. This is a quadratic function, and then 4 is just a constant. So we are going to say limit of x cubed minus x squared minus 4 is actually equal to limit of x cubed minus limit of x squared minus limit of 4 when x approaches 2, of course, in each case. So if you remember, we said that the sum of limits is equal to limit of sum, or we said that limit of difference of two functions is the difference of the limits of those two functions calculated separately. So that's why we can break this limit of this cubic function, this polynomial function, break it down into 3 smaller limits. So the first one is limit of x cubed. So that is going to be a limit of x when x approaches 2, all raised to the exponent of 3, because x cubed is a power function. So we know that limit of a power equals the power of the limit, basically. So we find the limit of x when x approaches 2, and then we raise it to the exponent of 3. Same thing with the other one. So this is actually limit of x when x approaches 2, and then the whole thing raised to the exponent of 2, of course. And then we have minus limit of 4, which, of course, I don't need to rewrite this, because limit of a constant is actually that constant itself. So this is actually minus 4. It doesn't matter if x approaches 2 or x approaches 2 million. It doesn't matter, because 4 is just a constant, and the limit of a constant is equal to the same constant. So we can even write this down somewhere. We can say limit of c when x approaches a is equal to c, and c belongs to the set of real numbers. So basically we're saying that limit of any constant number is equal to the same constant. And it doesn't matter if x approaches, any other number. Okay, so far we have used different properties of limits. So now we're going to say, okay, what is limit of x when x approaches 2? Well, that is very self-explanatory. It's going to be actually 2. I can even write this down. I can say limit of x when x approaches a is equal to a. So again, something very common sense. So we have 2 cubed minus, for the same reason, 2 squared minus 4. So that's 8 minus 4 minus 4. And the answer is going to be, of course, I believe 0, right? So the limit of this function, this cubic function, when x approaches 2 is equal to 0. Why? Because of all those different properties of limits that we used to show that this limit is equal to 0. So we used properties of limits. If you have not copied these two simple self-explanatory rules or properties of limits, you can also add it to your list. Okay, we found the limit of the function. This is another quotient here. So what comes to my mind is that limit of a quotient equals to the quotient of the limit. So I'm going to say this is equal to limit of the numerator when x approaches 3 over 2 divided by the limit of the denominator when x approaches 3 over 2 again, on condition that the denominator is not 0. So the limit of the quadratic trinomial at the bottom should not be 0. With that assumption, according to what authority did I write this? It is because of the properties of limits. Because we know that limit of the quotient of two functions is equal to the quotient of the limits of those two functions. It was one of the properties of limits, if you recall. And then in the numerator, I can say limit of sum of two functions is equal to the sum of the limits of those two functions. So we have a linear function, negative x, and a constant function, negative 3. So that would be limit of negative x, and then plus the limit of negative 3. And of course, x approaches 3 over 2, or whatever number given. The denominator, for the same reason, I say it's limit of x squared plus limit of x plus limit of 1 when x approaches 3 over 2. Clearly, because sum or difference of the limit of sum or difference of two functions is the sum or difference of the limits of those functions. So limit of negative 1 times x. So this goes back to the constant multiple rule, if you remember. It was one of the properties of limits. So I can write negative 1 times a limit of x when x approaches 3 over 2. We can bring negative 1 outside because that's playing the role of the constant. Limit of negative 3 is just negative 3. It's a constant. Doesn't matter if x approaches 3 over 2 or whatever. The bottom is going to be limit of x raised to the exponent of 2. Of course, x approaches 3 over 2. So limit of a power equals power limit. That's another property of limits. And then this one, it would be just 3 over 2. That one is just 1 because it's a constant. Limit of 1 is 1. Now, in the numerator, we have limit of x when x approaches 3 over 2, which would be negative 3 over 2 eventually, because that's 3 over 2. And in the bottom, we also have 3 over 2, but we have to raise it to the exponent of 2, plus 5 over 2, of course. If I continue, we get negative 9 over 2 in the numerator when you add them up. In the bottom, we have 9 over 4 plus 5 over 2. Okay. So this is actually 10 over 4. 10 over 4, 9 over 4, that's 19 over 4. And then we have negative 9 over 2. And if you reduce the denominators, it's going to be negative 18 over 19 end of the day. So that is the value of the limit of this rational function when x approaches 3 over 2. How did we get the answer? Of course, by using the properties of limits one by one. First, we set limit of a quotient equals to the quotient of the limits. Then we broke down the numerator. We said limit of sum equals sum of limits, or limit of difference equals difference of limits. And then we said limit of a power equals power of limit. All those properties of limits that we have learned in the past, we used them. Eventually, we got the answer. Okay? Now, you may be scratching your head. You may be saying, okay, is there a fast way of finding this answer? We know why the answer is negative 18 over 19. We know why the answer is 0 here. But is there a fast way to find the answer? Well, yes, it is correct. It is, like, there is such a fast method. And that is direct substitution method. So what you can do, you can say limit of x cubed minus x squared minus 4 when x approaches 2 equals. So what you can do, you can substitute 2 for x, of course, informally and discretely. You substitute 2 for x, that becomes 2 to the power of 8. And 2 to the 8 minus 2 squared is going to be like 8 minus 4, which is 4. And 4 minus 4 is 0. So by direct substitution method, you can get the same answer that we got before. But if somebody questions you, what are you doing here actually? Are you evaluating a function? Are you finding the value of f of x at x equals 2? You're going to say, no, that's not what we're doing. We are getting the same answer in a fast way called direct substitution method. But in reality, the reason why this limit is 0 is because of all those steps and all those explanations. The reason why that limit is negative 18 over 19 is because of all these explanations and all those application of properties of limits. That's the reason. However, informally, if you want to find the answer just very quickly, you can use this trick of substituting 2 for x, but you have to fully understand that we are not evaluating a function at all at a number like 2. That's not what we're doing, okay? It happens to be exactly the same answer. Now here, let's try this. So I'm going to find that limit. I'm going to substitute, I'm going to say limit of negative x minus 3 over x squared plus x plus 1, instead of writing a whole page, okay, using all those properties of limits, I'm going to just substitute 3 over 2 for x. So 9 over 4 plus 3 over 2, and see what this answer will be. So the top is going to be, that's negative 9 over 2. The bottom is going to be 15 over 4, 19 over 4. Okay, so if you work this out, it's going to be the same answer. So we see that the answer is again matching. And how did I get this answer? It was by direct substitution method, but we understand completely that we're not evaluating a function as a number. Okay, so this is like informal. You know, if you want to prove that the limit is negative 18 over 19, you have to use the properties of limits. So every single step here I used, you know, in this whole page solution, every single step I used, I referred to one of the properties of limits. I didn't just do it just like that out of blue with no reason. I was referring to specific properties of limits one by one when I was finding its limit. Okay. However, the fast way of finding that answer, you know, is by quickly doing the direct substitution. So whenever you're supposed to find the limit of any function, you can always try to see if you can find the answer by direct substitution. Okay, and if it didn't work, then you're going to have a plan B. You're going to go after another technique of limit computation. But if it did work, then at least you have the answer in like 2 seconds. Okay, and if somebody questioned you, said, why is this true, you know, then you have to show that whole page work. You can refer to those properties of limits and justify why the answer is negative 18 over 19 or whatever the answer is. Now, before I leave, I'm going to say, what is the limit of this function? X squared minus 4 over x minus 2 when x approaches 2. Okay? So I know you're going to say, well, just like before, we're going to quickly do substitution, you know, but we know what we're doing, obviously. So you do the substitution, you get 0 in the top and 0 in the bottom. And that's the moment that you are going to scratch your head. You're going to say, well, I didn't get negative 18 over 19. I didn't get 0. I didn't get a real number. So I got 0 over 0. What is this? Well, 0 over 0 is called indeterminate form. Okay? It's not called undefined. It's called indeterminate form. And whenever the limit of a function is in the form of 0 over 0 or indeterminate form, you have to find some sort of technique or method of calculation to get rid of this indeterminate form and find actually the limit of the function. If you have like a 0 divided by a number like 5 or whatever non-zero number, the answer is 0. If you divide that number by 0, the answer is undefined clearly. If you have a number divided by another number, like 4 divided by 2, that will be another number. But when you have the fourth case scenario, 0 divided by 0, then this is what we call it indeterminate form in mathematics. Okay, so a number divided by 0 is undefined. 0 over 0 is indeterminate form. 0 divided by a number is 0. And a number divided by a number, like 4 divided by 2, is just another number. So like 4 possibilities. Okay, in the next lectures, I'm going to teach you different techniques of limit computation, and I'm going to show you how we can calculate limits of those functions that are actually indeterminate form. Okay, but for now, try to learn direct substitution method and all properties of limits very well to the best of your ability. Thank you.